Alright, everyone. I'm a bit late. I only just got back, but it's time for Leetcode Weekly contest. Alright, let's go. I haven't had time to set up anything because I barely got here. Three and one. Alright, I got AC. I need to make it alternating. Okay. Let me move on to this question. If any number of beats. Oh, okay. Four, seven. AC. Okay. Actually, we'll just get a count. Alright, I just had to go close the door. Okay, the constraint is small, which makes it look like some sort of bit mask DP. I'm going to focus on this one first. just sort this. I want a default stick, not a... Alright, let's try that. 3, 2. Nope, that didn't work. Why isn't X and Y sorted? Oh, maybe it is. Okay. That is wrong. That should be that, I think. 3, 2. Right, I got AC. Okay, so naive seems slightly too bad. I wonder if I have to use all of the slots. Actually, I would always want to use all of the slots. The fact that the numbers are less than 15. I don't know what the complex. Like can get it down to this. Wait. 530 million is going to time out. Okay. We can have empty slots. Oh, it's not every oh, I didn't read this correctly. Okay. I didn't read this correctly. All right. Okay, that makes things like so much easier now. I misread the output slightly. Now I only have ones and zeros, and it becomes so much easier. Okay, now I have a better condition. So now I have up to 9 slots and 15 possible numbers. 66 million is still very, very scary though. careful. Okay, that didn't work out so well. B equals to 0, return 0. 7 and 8. Okay, that didn't work. And then 26. What is that? Okay, if you know if it's slot number. What? Okay, I misread this question so many times. I didn't read this question at all. In that case, I feel like I can just use the Hungarian algorithm. Like, I don't want... I did not read this question correctly, which is an issue. What's SciPy to optimize, I think. That's times 2. 0. For items. Like that. I did not read this question. I'm really sad. 3, 0. I wonder what this gives. I'll make that 1, 1, 2, 2, 3, 3. Okay, that's what I thought. Oh, okay, I think I was doing... let me just negate that and do that. 924. Alright, that was super slow because I did not read the question. My solve time is 22, which puts me here, which is not terrible. But it'll probably drop soon because that was a horrendous solve from me. Alright, I guess I'll go through the solutions now. Keep in mind that I think my Q4 solution is probably unintended, but I'll go through how I did it anyway. Okay, so for this question, this is just a brute force simulation. Basically, here I'm just swapping the two numbers to make sure num1 is always greater than num2, and then I'll simply subtract num2 from num1 and increment the number of operations I used. And then I'll print out the answer. The reason why this works fast is I think it's decently easy to show that at least every 2 moves, the maximum of the two numbers will decrease. Like, for example, if we have, like, let's say num1 is 7, num2 is 4. After we apply the operation, we're going to get num1 is 3 and num2 is 4. And you can see that the maximum of these two numbers has decreased from the max here used to be 7, and now the max here used to be 4. And every step, the maximum will always decrease. So if it always decreases, and the maximum started out at 10 to the 5, and at the end, and for the while loop to continue, the maximum of these two numbers has to be greater than 0. And since the maximum of these two numbers, that's the monotonic variable, since that's always decreasing, and it starts at 10 to the 5 and it has to always be greater than 0, then this loop can only run 10 to the 5 times. The only exception to this is, like, if they're equal, then the maximum of these two numbers won't decrease in one step. But then if they happen to be equal, then on the next step one of them will be 0, so the while loop will terminate anyway. And that basically explains why simulation works fast, and it's because the maximum of these two numbers always decreases, except when num1 equals to num2, in which case it terminates. Alright, let's go through this one. In this question, basically, this condition is basically saying all of the odd elements, all of the elements at odd positions have to be the same. All of the elements at even positions have to be the same, and those two numbers for the odd and even positions must be different. So, if we want to change, this is a very common thing to watch out for in Leetcode contests. If they're asking you the minimum number of operations for some condition to happen, it's usually easier to find the maximum number of elements that you don't have to change. And in this case, if we ignore about let's say we ignore about the odd positioned, the elements at odd indices for now, if we only consider the even ones, if we were asked to find the minimum number of operations to make all those numbers equal, then I would try to find the maximum number of numbers that I don't have to change. And in this case, I would clearly just choose the element that appears the most frequently, because that frequency would be the number of elements that I don't have to change. And yeah, that's basically what I'm doing here. So basically, this part is just generating like a frequency hash map. It's each of the key value pairs, the keys corresponds to an element, and the value corresponds to its frequency. And I'm building one frequency counter for both the odd and the even indices. Ignore this for now. Then I'm sorting each of the frequencies and the elements, and I'm trying to find the most frequent one first. And ideally, what I'm going to do is, the number of elements I don't have to change is simply x00 plus y00. Here x00 is the frequency of the most commonly occurring element of the even indices, and then y00 similarly is the frequency of the most frequent element for the odd indices. And ideally, the number of elements that I wouldn't have to change is the sum of these two, and therefore the number of ones that I would have to change is the total number of elements subtract the number of elements that I don't have to change. And that works when the odd and the even, when the most common element for the odd indices is not equal to the most common element for the even indices. The problem is because of this condition that says that the odd and the even elements have to be different, it's not so straightforward. So basically the workaround to this is either, you can show that either I will take the most common element for the even indices and the second most common element for the odd indices, or the other way around, I'll take the second most common for the even indices and the most common for the odd indices. And yeah, that's basically my code. Here I'm just putting this into my table just in case these default dicts happen to have only one element. Like if there was only one element in this, then if I tried to access an index out of bounds, that wouldn't be nice. So I just add this to my defaults dict just to make sure it has at least two elements in the frequency. Okay. What was this question again? Oh, okay. I think this question is probably easiest to go with an example. Let's say like my bag looks like this, and let's just say that none of the bags will be empty. Like in my solution, I'm guaranteeing that I don't want any empty bags. Then how can I find out what the answer is? Well, clearly, I have to perform operations, which is decrement an element, and I need to make all of the elements equal. And in order to do this, clearly to minimize the number of elements, I should just make all these elements equal to the minimum. So for here, the number of operations I would do would have to be the sum of this list subtract the minimum of this list, which in this case that happens to be which is 22 in my case. But the other thing is we don't have to make all of them non-empty. What if I guaranteed that we were making exactly one of them non-empty? Well, which of them would I want to make non-empty? Clearly, it doesn't make sense to make something like 8 non-empty, because I would have to decrement this 8 all the way down to 0, and I would have to get all the elements to the right still to 4. In fact, the only thing that makes sense is to take the smallest element and make that one the empty one, and that way all the other ones to the right will be decremented to this element, which in my example happened to be the same. But it doesn't have to. Like it could just be like this. So another alternatively is the sum of these elements subtract the min of those elements, and then I would have to add on my 3 because I decremented the 3 to 0. 18, that's 21, so that would actually be better. And then now I can ask myself, what if I took 2 empty bags? And you can basically see that anytime I'm taking x, I'm making x of the beans, bags, x of the bags empty. I should choose the x smallest ones and make those empty. So basically, my implementation is ever so slightly different to what's here. So similar to the previous question, instead of minimizing the number of beans I remove, I can maximize the number of beans that I don't remove. And then, so M will store the maximum number of beans that I don't have to remove. And then I simply return the total number of beans to begin with minus the number of beans I didn't have to remove. And basically I'm iterating over all prefixes of beans once I've sorted it, And I'm asking for each prefix, what happens if I made that prefix empty and I made everything else in the other suffix non-empty. So for a given I, I'm basically saying I'm going to make the first I bags empty and all other bags non-empty. So in our case, the number of beans that won't be removed is simply beans I times this number. This number comes from the number of non-empty bags, and this number comes from this number will be the minimum. This will be like the final number of beans in each of those bags, because the number of beans in each of those bags will have to be the minimum. And yeah, that's basically my code. And then finally, there's this question, which I just I didn't read this question correctly, I'll be honest. I misread this so many times. I assumed it would be like the minimum, you'd take the AND of two numbers in the slot. I didn't realize you took the AND with the slot number. So I'm assuming this is some sort of bit mask DP, but I did something slightly different. Basically, let's say that we have let's say we have 4 slots and the numbers are like 1, 4, 6, 8, 10. Okay, 2, 3, 5, 2. Then basically, I have 8 available numbers in the slots, and what I can, so I have 8 different possible. Since I have 4 slots, I can fit 8 numbers inside, and these basically the slot numbers that I have available are 1, 1, 2, 2, 3, 3, and 4, 4. And each of these numbers appears twice because each of the slots can hold two of the numbers. And basically what I'm trying to do is I'm trying to assign each of these numbers into one of these slots such that none of these two numbers get the same slot. By slot, I mean like each half slot almost. I'm sort of dividing each slot into 2 separate sections, and then I'm trying to assign each of these numbers to a section. And the value of a number when it goes into a section is just equal to the bitwise AND of that number with the section. So for example, if I assigned this number 1 to the first section in the slot 1, and I assigned this 4 to the first section of the second slot in the second section of the first slot, and so on. If I did this assignment, then my total value would look something like this, and so on and so forth. But of course I don't have to match this number with this section, this number with this section. I could assign this one to that one, this one to this one. Basically, I just need to permute these numbers, and then I can just take the bitwise AND of corresponding elements. And you may notice this problem. This is called like the assignment. I think it's called the assignment problem. Basically, we need to allocate. We need to like permute these 2 arrays and match them up such that some cost function between these 2 elements is minimized or maximized. So in this case, what if I constructed an 8x8 array, 8 list, where like array xy equals to numbers x and the bitwise AND of that with the slot number y. So here these are my numbers, and here these are my slot numbers. So let's say I generate this 8x8 list, where this list is basically having the cost function or the value function, where I'm saying if I matched up the x number with the y slot number, and then what value would that contribute to the total? And essentially, What I'm trying to do is I'm trying to find, this will give me 8 by 8 list, and I'm trying to find 8 different cells where each of these cells has a different row and a different column, and I'm trying to maximize the sum of those values. Like, if let's say I had a smaller case, which was like, let's say I had a 3 by 3 list like this. This is not actually something like this. Let's say I had a 4 by 4 list like this. I would be trying to select 4 cells with different rows and different columns, because each of these rows corresponds to one number, and each of these columns corresponds to one slot number, and I need to match the numbers with the slot numbers. So for example, if I chose this 3, this 2, this 1, this 8, I'm basically choosing the assignment: put the first number into the second slot, put the second number into the first slot, put the third number to the third slot, and put the fourth number to the fourth slot. And then the total value would just be the sum of these cells. And this is a very famous problem. I think it's called the assignment problem. Can't quite remember. But anyway, there is a trivial, not trivial, there's like a well-known way to do this, and using bitmask DP. So the DP is which row we're up to and which columns we're able to take. And I'm just going to, okay, there is a bitmask DP solution with the complexity is the number of rows times the number of columns times 2 to the number of columns. And okay, let's analyze how many rows and how many columns there are. Since there might be like 2 numbers and 8 slots, what I did is I'm just going to pad the number of numbers with zeros, such that in my list I have the same number of rows and columns, because it makes the assignment problem a little easier. And because I can just fill it with 0, because 0 and anything is 0, so it won't affect my sum. How many rows can I have? Well, the number of columns I can have is simply the number of slots times 2. And that means that the number of rows can also be the number of slots times 2. So the number of slots in this case is, the number of slots is times 2 is at most 18. That means that I can have an 18 by 18 list. And now that I have an 18 by 18 list, I can simply do my this DP. I'm not sure if this is going to run in time, because I didn't actually do this. 8493. So that's about 84 million possibilities, which I'm not sure if that would pass on Leetcode. I'm assuming it would with like C++ or something. Anyway, basically in Python, there is this module called scipy.optimize, which for some reason Leetcode lets you use. And then linear sum assignment is just a function which does this for me. And the cool thing about this is this uses, it's not quite, I think it's like a modified version of the Hungarian algorithm. But basically the Hungarian algorithm is an algorithm that solves this problem, not in exponential time, but it solves it in like O(n) cubed time, where like n is number of rows and columns. So in like my case, this would just be O18 cubed, which is good. So that way I don't risk timeout at all. And I'm negating it, and then I'm negating the answer as well, because by default linear sum assignment computes the minimum, and I want to find the maximum. There is some argument I can put here to make it the maximum, but I can't remember off the top of my head what that is. So that's why I negated everything and then negated the answer. Anyway, that's my solution for that problem. Now let's go see how I am in the standings again. Okay, I got rank 10, which is pretty nice. I haven't had a good performance in a long time. And even though I misread so much, I probably could have gotten like about here-ish if I didn't misread it. Anyway, I haven't had a good contest in quite a while, so I'm quite happy with that. Anyway, that's all I have for you today, and thanks for watching.